Good morning, everyone. There seems to have been a little bit of an error with our fonts translating over from Canva, but this is our group. For our summer research connection project, we made gradient condensers and studied air ion concentration.
Hi, I'm Daniel Sim. I'm a rising senior at Polytechnic.
I'm Violet Beach. I'm a rising senior at Pasadena High School, and our mentor was Robert Morgan, and our teacher was Alexander Gutierrez.
I'm Madison Blahon. I'm a rising senior at Marshall Fundamental. And our goals for during our research were to learn about the concepts relating to and the theory behind the gradient condenser. Then was to build our own condensers, build gradient condensers under our mentor, and to test the Leonard effect at a local waterfall and conduct further experiments on ion concentration using our gradient condensers.
And you may be wondering, what is a gradient condenser? It is the standard device used to measure air ion concentration, and it is used for many different things, including analyzing the atmosphere, testing water quality, understanding biological processes, and many more. Recently, these devices have inspired new designs for things that could solve the long-standing problem in plasma physics, including which is measuring atmospheric pressure plasmas. And our gradient condensers analyze atmospheric air density, ion density, using two electrodes with a voltage bias that attracts the ions and creates a current that we're able to send through a circuit, which turns it into a voltage, which is very small, so we must amplify it to a readable voltage.
So there are challenges to building a gradient condenser. The first one is radio frequency interference. For example, when you're playing music on your car and you listen to the radio, there's actually radio frequencies traveling from the radio station to your car, and the wires from the gradient condenser could actually pick up on this, which could interfere with the signal. And using aluminum foil, this can minimize the effects of the interference. Another one was a small current. So the currents from ions are very small, around 10 picoamps. And with operational amplifiers, they can accurately amplify the signal current. Another one was the fact that we were only measuring a fraction of ions. Since we were measuring a very small amount of ions, we needed to use a single capacitor, which involved applying a sufficient voltage bias to the outer electrode, which would excite most of the ions to the inner electrode.
Before we could begin building our gradient condensers, we had to learn about new concepts and how to work with new tools, including equations like Ohm's law, which proved to be very important, and how to work with breadboards, resistors in both series and parallel, soldering irons, and operational amplifiers. Working with operational amplifiers was very difficult. It personally took me about 3 sessions, like 9 hours to get it to finally work. And we had certain issues like on field, a fan shorting out with no replacement, which we had to include in our data and work around. And in efforts to calibrate our circuits, sometimes it actually made our offset worse. So another thing that we had to just work with in data analysis.
Another one of the construction challenges was filtering out noise and radio frequencies. As mentioned before, the radio frequency can interfere with our gradient condenser, and by applying aluminum foil with either electrical tape or hot glue, it would prevent all those frequencies. Another one was the potentiometer sensitivity. It can go from 0 to 1 mega ohm. And when I was first testing out my circuit, the potentiometer started smoking. And reviewing the circuit and after turning it off, I realized that I used the wrong resistor values.
Okay, so this is I'm going to explain the detector element of the gradient condenser. It's kind of hard to see, but the detector element consists of 2 separate copper tubes. We apply a potential difference across these tubes. This potential voltage difference creates an electric field in the space between the tubes. This electric field in turn accelerates positive ions in the atmosphere towards the inner tube. These ions, when they strike the inner tube, create a current in the inner tube that we can then measure with the amplification circuit. This current is, we can derive the atmospheric ion concentration from the magnitude of this current. To this equation, it's actually impossible to see, but it's where the current is equal, where the concentration is equal to the current divided by the charge of one electron multiplied by the airflow rate through the tubes. And it's important to keep the airflow rate between the tubes constant so that we don't get fluctuations and readings further on. So to keep the airflow rate constant, we use electrically powered fans. Oh, that it just keeps getting worse. This is the calibration stage. And so in any electrical circuit, there will be small voltages present between connections and in our circuit inside the internal circuitry of the operational amplifier. Normally these are negligible. They're on the scale of 10 microvolts and they're not even detectable on a multimeter. But because we're amplifying these voltages by such a large amount, they will be amplified enough to actually drown out the actual signal. And so it's important to cancel out these offsets through the calibration circuit. Calibration circuit is powered by a 4.5 volt battery, and through this resistor network allows us to feed anywhere from 0 to 10 millivolts in order to cancel out any offset of that circuit. Second stage is the transimpedance amplifier, and as you'll recall, the detection element uses a small current, but the issue is we can't amplify current as easily as we can amplify voltage. So we need to convert that small current to small voltage. We use the op amp to convert the current into the small voltage with low impedance. And this stage produces an output voltage equal to epsilon, which is the voltage, which is the error voltage that should hopefully have be zero because of the calibration, minus the input current times 10 to the 6th. And the 10 to the 6th comes from the 1 mega ohm resistor, so it's an ohmic amplification. And the final stage is the inverting amplifier. Voltage from the stage 2 is actually still too small to be detected by the multimeter. So we need to again amplify it by a factor of around 100. So we're going to use an op amp. Op amps can supply theoretically infinite amplification, but in order to get a reading, we can actually use we use a negative feedback loop to limit the amplification to around 100. This is an inverting amplifier, so the amplification factor is equal to the resistance of the feedback resistor. That's the topmost resistor divided by the resistance of the resistor on the left. And so for this particular implementation, the amplification factor is 100, but it's inverting, so it's negative, so the amplification factor is negative 100. This is the full circuit diagram, and looks like I've again been messed up by Canva, but the combining the amplification of the transimpedance stage and the inverting amplification stage, we get that the V out is equal to the equation on the bottom. And what's important to note is that epsilon is not amplified by the factor of 10 to the 6th, it's only amplified by the factor of 10 to the 2nd. And so that means that we're avoiding amplifying the error wherever we can. Okay, so these are some images of the Gurdon condenser, and the tinfoil box on top is where the tubes live. It's shielded to avoid EM interference, and the fan is there to provide that constant airflow.
So the main thing that we measured with our Gurdon condensers was the Leonard effect at a waterfall, which is water molecules impacting, like hitting each other so hard that they release electrons. So before beginning, on the bottom right, you see that's our calibration sheet, where we just got our baselines to eliminate any error. And so our data matched up with other trials, and we were seeing points of like the same magnitude as we got closer to the waterfall, but that could be due to the humidity and the wind generated by the waterfall. And as we got farther away, our values reduced down to our baselines, which created, this graph here. We measured about every meter, and, it,
So we're seeing a power law relationship with the ion concentration, and that's consistent with ion flux being directly proportional to the surface area of, for instance, a cylinder, if you're treating waterfall as a line source of ions. The certain proportional, the ion flux would be at a certain distance will be proportional to the surface area of the cylinder with that radius.
So the Tesla coil generates very high voltage and arcs of electricity are formed, which can propagate through the ionizing air. The power generator of the Tesla coil causes significant noise, around 100 millivolts. And the Tesla coil is going to modify the chassis on the ground, aka the ground of the box, which affected the measurements. The ion concentration was calculated by subtracting these. So on the graph, as you can see, we met for our first trial, we did a 5-second interval. And compared to the waterfall, there's a higher ion concentration, and it's generally constant with only 0.1.
So this is data taken from Alaska tower fan that claims to have an ionization mode that produces negative ions. The fact that this produces negative ions is significant because in the original configuration, the Grignard condenser can only detect positive ions. If you recall, the electric field repels positively charged atmospheric ions away from the outer tube and towards the inner tube, and that's what creates the current. But negative ions will be attracted to the outer tube and not strike the inner tube, which is the detection element, and therefore not create any signal. So therefore, we need to reverse the voltage biasing on the copper tube so that the outer tube is negatively charged instead of positively charged, and the electric field will accelerate negative ions and electrons towards the detection element. This data exhibits a very strong linear trend that is consistent with a very slow rate of ion production. But if you look at, so that's the blue line. If you look at the red line, so again, this is over a time of minutes, so this rate of production is very slow. But if you look at the red line, that is without the fan, and you can see that the baseline is actually drifting. And so if we subtract the baseline drift away from the observed increase, we can determine that the fan seems to produce around 40 ions per cubic centimeter per minute. But more research is needed because in order to know more because of this baseline drift. And also outliers with this.
So we measured the ionization of a candle, and since the flame is very small and not super hot, it did not increase ion concentration by much, but it was still measurable. So we did see a slight increase, which was expected, but what we were able to gather from this is that it was about 10 times more than our baseline and 10 times less than the data that we gathered from the waterfall. And so we measured about every 5 seconds, and the data is very scattered, but it is most likely due to noise. So we were able to build gradient condensers and use them to measure the ion concentrations surrounding atmosphere of different ion sources, which we presented in this table in order from greatest concentration to least greatest, with ambient obviously being at the last. And I'll let you take the test.
All right, so as you noticed, the Tesla coil has the highest amount of ion concentration, and this is because of the lightning coming out of the Tesla coil and the high voltage.
What we're seeing is what we expected. The candle obviously sits above the ambient and under the waterfall, and the waterfall because the Leonard effect isn't in itself very powerful, but because of the fast, nature of the waterfall, it's a wide cylindrical, thing of water, like it's just a lot more powerful than if you were to say measure a fountain. So we expected it to sit definitely below the, Tesla coil, but once again, above the candle because it is a lot more powerful than the little flame.
So the ionizing power fan out of these ion sources is by far the weakest because it's actually barely above ambient. And so that's what we were expecting, but what's important to note is that the ambient ion concentration we measured is actually an order of magnitude greater than what we expected from research literature and the like. And this is likely due to the very large swing in noise ratio, could be caused by a variety of factors, EM interference, voltages within the circuit. But the point is the signal to noise ratio at ambient is very high, and therefore ambient readings that low are kind of iffy.
As the concentration levels decrease, the error increased. Any questions?
Great presentation. I love your field trips that you took. This is a silly question, but what would you measure with your gradient condenser that you, like, what would each of you measure if you could?
If I could, I would probably want to take more measurements on the Tesla coil because we had some weird issues with the power source on the Tesla coil itself creating noise, and then the Tesla coils high voltage influencing the grounding on the box, which throws off your measurements if your 0 point is constantly moving. But we definitely want to see what kind of ion field the Tesla coil generates.
I want to measure sorry, I'm a little bit nervous. I want to measure just different like waterfalls, smaller like fountains, smaller waterfalls, just so to see the point at which there's a significant increase to see the effects of the Leonard effect in action, you know.
Yeah, so probably wanna, as Nia said, probably wanna measure on the Tesla coil. Like to, maybe run more tests just to see if the measurements would be different. So,
Is there a specific reason why we chose the ion sources? Yeah, so our mentor Robert told us to all go home and find something that we wanted to measure. And so, Enio brought in his ionizing tower fan. And I was unable to, bring in something, so I used a candle because that was being measured on the first day. And I was really curious about that, so I wanted to test that out and see how it worked. And, we all got Tesla coils to build at home, and so that's what Addison chose to do his measurements on. Thanks for the question. All right.
Any quick reflections for what you?
Your favorite part.
Yeah.
My favorite part was probably working with the group, getting my hands a little dirty, you know. I haven't really put my mind to use like building something in a while, other than like robotics at school. And this was just definitely a learning experience for me, and that's what I appreciated the most about it.
yeah, I enjoyed being with my group, and they're very kind and respectful. But my favorite part of the program was probably learning how to solder. I've seen YouTube videos of people fixing stuff and sometimes soldering. So it was great to know that. Also, the current test was second.
So, my favorite, I guess one of my favorite parts of the program was figuring out how I was going to measure if the tower fan is actually producing ions. So, because Like I was measuring it with just the normal setup, and then I realized it will produce negative ions. We can't actually measure those, so I had to swap the voltage bias, and that's when I started getting into the kind of the process of engineering stuff. I had to actually shield one of my wires in aluminum foil in addition to just shielding the box because I was getting so much interference. The process of kind of iterating and problem solving is my favorite part of the program.